Alright, let's do a very simple example problem from section 5.2. So here it is. Here is the example problem. We have an operational amplifier. Okay, there it is. There is your operational amplifier, and then the operational amplifier has some circuit built around it. And the problem says it has two parts. The value of Vs is given, okay, the input voltage that is applied to the negative terminal, that is given. Now, we are supposed to find out V out. That is first part of the problem, right? Now, there is a second part to the problem, which is find the range of Vs required to avoid saturation of the OpAmp. Okay, so we are going to look at both those problems, both those parts of the problem. First example problem. The question is, where do we begin? If you are given a problem like this with an OpAmp circuitry, how do you begin? Well, let's demystify this. We are going to apply all the theory that we learned so far in section 5.2. Okay, now let's see the first step. So when you're trying to work on a problem like this, the first step number 1 is you make sure, confirm there is a negative feedback. If there is negative feedback present, you can assume linear region. We are going to verify that later on. But let's see, how do you confirm there is a negative feedback? Well, take a look. The output is tied back into the negative terminal of the input of the OpAmp, right? So there is a negative feedback. That is how we define negative feedback, right? The output is fed back into the input, into the negative terminal of the OpAmp. That's negative feedback. So yes, there is negative feedback present, so we can assume linear region. Okay, now step number 2. Okay, you can follow these general steps pretty much throughout the analysis of all problems that you see in OpAmp. So let's take it very slow. Okay, step number 2 is really write KCL. At Vn. Okay, what does it mean? Let's go back to my operational amplifier and identify what is Vp and Vn. Okay, so here is my OpAmp. That guy, remember? That guy is Vn, the voltage on the negative terminal. Okay, this guy, that guy is Vp. Remember? That's the Vp. And of course, V out is here. V out is over there on the right hand side. And I interchangeably refer to V out as Vo and use these two terms interchangeably. Now, so step number 2 is to identify Vn, which is that guy, that's my Vn, and we want to write a KCL there. Okay, step number 2 is to write a KCL at node Vn. Okay, let's see, at node Vn there are how many currents flowing? There is one current, okay? There is another current leaving that node. And let's not forget the third current, IN. Okay, everybody with me? So there are three currents, three branch currents coming out of that node. Okay, when you write KCL at that node, you add all the currents and equate them to 0. Okay, let's see what is the current here going from the node to the left. That will be Vn, which is the node voltage there, minus Vs over this resistance. Okay, so 16 kilo ohms. That is the current flowing from right to left. Okay, it's going westward. Okay, that's the current flowing in the westward direction. Okay, now let's see. Let me draw this back. Okay, there it is. Now, that's one current. The second current is the current going in the northward direction. Okay, that's the current flowing in this branch. Okay, what would be that current? That current would be Vn minus Vo, which is the voltage here. Okay, Vn minus Vo by 80 kilo ohms. That is the current flowing in this branch. Okay, that's the current flowing in this branch. And of course, there is a small IN shown here. If I am to write the KCL, I have to sum these three currents. Okay, this guy. So cut that and paste it over here. That's the current. Remember, that's the current flowing in the westward direction. Okay. Now, then add that to this current. Okay. Add that to this current. So that guy, we want to paste it here as well. Okay. Plus, there is another branch current IN, right? There is a small current IN. So all of that should equal 0. That is the idea of KCL, right? The currents. All I did was to sum all the currents leaving that Vn node and equate that to 0. Okay, KCL at node Vn. So that's step number 2. Okay, let me put that in black. Okay, so step number 2. If you want to name this equation, you can number this as number 1 if you so choose. So step number 1 is to confirm that we have a negative feedback. Step number 2 is to write KCL. Now let's see step number 3. Is apply the voltage and current constraints. Okay. Now, voltage and current constraints, I gave them as 2 rules. Rule number 1 is that Vp equals to Vn equals to 0, or Vp equals to Vn. Okay, that's the virtual short. And rule number 2 is that Ip equals to In equals to 0. Okay, you don't remember that? Go back to my notes and then look at the rules that I have given, ideal op-amp assumptions. They are also called voltage and current constraints, right? There are two rules basically. Vp equals to Vn, Ip equals to In equals to 0. Okay, so we are going to apply those rules really quickly here. And I told you that this simplifies our analysis quite a bit, right? Let's see. So we are going back to the problem, looking at this. Okay, let me copy this equation, equation number 1. Okay, let's see. Now I'm going to apply rule 1 and rule 2. Vp equals to Vn. Well, what do I know about Vp or Vn? Let me go back to this problem. The problem, sure enough, Vp is tied to what? Is tied to ground. Okay, Vp is tied to ground, right? So Vp is 0, and because Vp is 0, Vn also turns out to be 0, right? So that's the idea of virtual short. So we are applying a bunch of concepts that we saw in section 5.2. Okay, because Vp is tied to ground, by definition, Vn is also at 0 potential. Okay, this is interesting. Now, the other rules is that Ip and In are 0. So here is what is going to happen. Vn is going to go to 0. This term, Vn term, is going to go to 0 as well. So this is going to go to 0, this is going to go to 0, and this guy is going to go to 0 as well. That simplifies the equation quite a bit. Okay, now 0 minus Vs over 16 kilo ohms minus V naught over 80 kilo ohms, and this turns out to be 0. Okay, so this equals 0. All right, now let's see. You can rearrange this equation because we are interested in finding VO. Remember, that's the first part of the problem. The first part of the problem is to find the value of VO if Vs is given. Okay, so we are manipulating this VO over 80 kilo ohms and taking it to the other side of the equation. Okay, and then leaving this minus Vs over 16 kilo ohms on this side of the equation. Okay, so it turns out that VO really is 80 kilo ohms by 16 kilo ohms multiplied by negative Vs. There it is. You see, the secret is in applying these rules. When you apply Vp equals to Vn, you see that Vp is tied to ground. Therefore, the Vn term really nicely goes to 0. Okay, when you apply the second rule, Ip equals to In equals to 0. Okay, that's called the current constraint. When you apply the current constraint, that In term drops to 0. So these are rules that are helpful. So V output, therefore, is 5 times negative Vs. Okay, of course, the value of Vs is given. What's the value of Vs? It's given to be 2 volts. Okay, the value of Vs is given to be 2 volts. Therefore, V output equals to 5 into negative 2. Therefore, that's negative 10 volts. Okay, one last step. Okay, so so far we applied 4 steps. The first step is to confirm negative feedback. If there is negative feedback, assume linear region of operation. Then write KCL at the inverting input terminal. Then apply the simple rules, simplifying rules. Now, step number 4 is verify that V output is less than positive VCC and greater than or equals to negative VCC. Okay, so you want to make sure that your power supplies are setting the limits for the output that you arrive at in the answer. Or in other words, I have forgotten to give you these numbers. The plus VCC was plus 10 volts and the negative VCC, the negative power supply, is negative 15 volts. Okay, that's something given in the problem. Okay, now you see that the output that you calculated eventually, which is negative 10 volts, that's the answer you solved for V output. That is indeed in between the positive and negative power supplies. Okay, remember, if not, the V output saturates. Okay, so we assumed that this op-amp was in linear region, and in fact the 10 volts, the negative 10 volts answer that we received, that we saw for V output, is within the output, within the power supply values. Okay, hence the answer is this guy. Okay, that's your solution to part 1. Okay, the output VO is negative 10 volts. All you have done is to apply these steps. Step 1, step 2, step 3, and step 4 is the confirmation. We want to verify that the output calculated is within the power supplies. Okay, now let's see if we can solve the second part of the problem. Okay, the second part of the problem really says, what does it say? Find the, let me copy this, find the range of Vs required to avoid saturation. Okay, so find the range of Vs required to avoid saturation. The idea is, if you think about it, as long as V output is in between plus VCC and negative VCC, okay, then you are in linear region. If not, you are in saturation region. So this is the condition that ensures linear region of operation. Okay, this is the condition that ensures linear region of operation. So really, you want your V output to be greater than or equals to your negative power supply, and you want your V output to be less than or equals to positive VCC. Okay. Now, you know the value of negative VCC, which is negative 15 volts. Okay. And VO is of course negative Vs times 5. Right. That's what we saw. V output is negative Vs times 5. Right. So that's what I'm plugging in. You want to make sure that your Vs times 5 is greater than or equals to negative 15. Okay. So if you multiply by negative 1 on both sides, 5 times Vs should be less than or equals to 15 volts. This inequality is flipped because you multiplied by a negative 1. Therefore, Vs should be less than or equals to 3 volts. Okay. Let's see what happens on the positive side. You want to make sure that VO is less than or equals to plus VCC, which is given to be 10 volts. Right. So 5 times negative Vs should be less than or equals to 10 volts. Okay. Multiply both sides of the equation by a negative 1. 5 times Vs should be greater than or equals to negative 10. Therefore, Vs should be greater than or equals to negative 2 volts. Okay. Now, you have all the information that is needed to answer the question. What is the range of Vs? Well, Vs should be in between negative 2 volts and 3 volts to avoid saturation. Okay. So, I'll make it really quick and show you. So, this will ensure linear region. Okay. Let's pick an aside to this problem. So, we are going to go on a little expedition to see what happens if Vs is greater than 3 volts. Let's say I want to pick a value of Vs equals to 4 volts. Okay. Now, if I try to calculate the value of VO, which is negative 5 times Vs, right? That's what we figured. V output is negative 5 times Vs. Now, see what happens. V output is going to go to negative 5 times 4, which is negative 20 volts. You see the problem? Do you see the problem? This cannot happen because the power supply is negative 15 volts, right? Your OpAmp cannot supply below the negative VCC. Remember? That was the saturation region. So, this indeed proves that if you pick a value of Vs that is greater than 3 volts, then you are in saturation region. Okay. So, let's pick another value. Let's pick a different, let's pick a value Vs to be negative, I don't know, it should be negative 5 volts. Okay. Let's pick a value for Vs equals to negative 5 volts. If Vs equals to negative 5 volts, that makes VO what? Negative 5 times Vs, right? So, which is going to turn out to be V output is going to be negative 5 times negative 5, which is going to be 20 volts. Okay. Is that possible? V output equals to 20 volts? That is not possible, remember, because the maximum, V output maximum is set by plus VCC, which is only given to be positive 10 volts. Therefore, if Vs is not within these limits, negative 2 volts or positive 3 volts, then you're going to be in saturation. This guy ensures a linear region of operation. Okay, so to recap, what we have done is to follow 4 simple steps. These steps you can apply over and over again when you are solving problems. Okay, then to solve the second part of the problem, all we did was to make sure that your output voltage is within the positive and negative power supply. Okay, once you solve that, you get numerical values for the limits of the V source. Okay, we'll stop there. It's a really interesting problem. We'll look at more example problems later on.